Are you interested in having a stable temperature measurement from the sintering zone, analyzing the influence of the main burner flame on quality, anticipate clinker quality changes, having information about temperature distribution over the time at the sintering zone, burner tip and coating, finding always the optimal main burner settings, analyzing emission changes in their correlation to the main burner flame, increasing the alternative fuels rate? If you answered yes to one of those questions, have a look at Powitec's Thermography pit indicator. The pit indicator consists of an optical sensor on a retraction unit and a sophisticated software. It provides you with thermographic images and a video. The optical sensor is mounted on an automatic retraction unit, which retracts the sensor in cases the sensor is in danger of getting damaged. This sensor consists of an endoscope protected by a high alloy steel tube which is entering the kiln. This tube is cooled by air or water, and the endoscope tip is kept clear by purging air, building an air bubble in front of the protective lens. The light beam goes through the endoscope and is splitted to a digital camera with an onboard PC and the video camera. This housing can be water cooled as well. To control the temperatures, air and water flow, as well as the retraction unit, the system comes with a field cabinet, which even can contain a monitor to show pictures of the flame. The pit indicator comes as well with a system computer and a sophisticated software. Process control data can be displayed within the software with a process connection. Temperature measurements and threshold values can be written to the PCS. An internet connection allows for direct service of Powitec specialists via remote control. But let me show you some of the capabilities of this product more in detail. The pit indicator shows videos, a screenshot here on the left, and as well a thermographic image here on the right. In the middle, you see a comparison with a pseudo-color picture produced by an outdated technology. The Powitec thermogram is a matrix of totally 440,000 quotient pyrometers, and the result, the temperature, is shown as an individual color in the matrix. Each color reflects the temperature as the scale on the right is showing. Blue colors are around 800 degrees Celsius, orange colors are around 1400 degrees Celsius, and white colors around 1800 degrees. This clear picture can be achieved through a patented electronic dust filter. Let me introduce you to Powitec's digital image processing in rotary kilns using the adaptive electronic dust filter to reduce dust impact on pictures. In a typical rotary cement kiln with a grate cooler, the burnt clinker is dropped onto the grate. Secondary air from the cooler is used for heat recovery reasons, but it as well transports dust from the cooler into the kiln, disturbing the view on the flame. Harder or hotter burning causes more dust. Images get dark, and classical pyrometer's temperature drops. Powitec's integrated shutter mode acquires high-resolution pictures with varying exposure times from 1/10 of a second to 1/10,000th of a second. An extensive image source is collected over the time, and the sophisticated software makes a selection of the 25 pictures taken per second. The AEDF selects those pixels offering the best contrast and brightness. The selected pixels are merged into a single image, which becomes the information source for RGB thermography and pattern recognition. Depending on the dust load, a new picture is shown every 1 to 10 seconds. Let me now show you how you can read the flames and read temperature development over the time. For this, Powitec invented the polyline. The thermographic image is measured along a selected area termed polyline. Those lines, which can be straight lines or polygons, are drawn onto the thermogram to measure, for example, the flame diameter and flame length, as well as the plumb and ignition point. The polylines are automatically transferred to a time axis every second as the image updates. With the passing time, the copied polyline indication scrolls to the left as the most recent polyline is entered at the far right position of the axis. The same thing is done with the other polyline, indicating burner tip temperature, plumb length and ignition point. The resulting chronological display of the local temperature distribution offers a fast and reproducible geometric indication of the main burner flame patterns as well as of the conditions in the sintering zone and the clinker bed. Even smallest flame variations are visualized. The time axis can be changed, and so the polylines can be displayed in this diagram over a few minutes or even over days. This is how it looks like in real life. This customer has installed a burner with two tubes, one for the primary fuel and one for the alternative fuels. As you can see, the polylines are moving from right to left and are indicating a massive change in the flame. The upper polyline shows the vertical flame diameter, and the lower polyline is banded and shows the coating, the flame diameter, and the lower burner tip temperature. Those graphs show the mean temperature of defined regions. These regions are defined in the image as squares. The red line shows, for example, the mean temperature of region 1. This is another example of a thermography. This customer has installed a two-screen solution. On the right side you see the flames as a thermographic image. On the upper left screen, the average temperatures of the defined regions are indicated. And on the lower left screen there are two polylines. The upper one is showing the horizontal line and the lower one is showing the vertical line. Though this customer only burns coal, you can see how there are changes in the flame. Here the flame is smaller and cooler, here the flame is wider and hotter. You as well can see that the plumb is getting longer over the time.